So in the last class, we were discussing about basically about what are images, okay, and what are the different filters that can be used for various tasks. Okay, so I'll just have a quick revision on that, and then we'll move on to the remaining topics on sharpening spatial filters. So can anyone tell me what are grayscale images? Yes, anyone? Adarsh, are you there? Could you tell me what is a grayscale image, or what do you mean by grayscale image or gray level intensities? Okay, I'll call out names one by one. Okay, I see that there's a in the chat. Okay, Vansh, an image where all pixel values are represented by values between 0 and 1. Okay, 0 and 1 if it is a normalized image, or depending upon what is the k-bit image, the maximum intensity value. Let's say if it's an 8-bit image, if it's 256, then you have values between 0 and 255. Okay, so basically in a grayscale image, it's all about it's an image, a monochromatic image, where you have different varying levels of grayscale values, right? And gray level intensities are the that particular pixel intensity levels, okay, which is present in a grayscale image. And if it is a k-bit image, then the intensity value of that k-bit image, the number of intensity levels that you can have is 2 raised to k. So these were some of the things that we discussed. And histogram. Can anyone tell me what is a histogram? Histogram of an image. What do you mean by histogram of an image?
It shows the blacks.
Could you repeat again? I didn't hear you.
It shows the whites and blacks of the image, like wherever the depending on the pixel.
Okay, it's basically a plot of how many pixel value, how many pixels are present in an image with a particular value, right? A particular intensity level. So again, if you're taking an 8-bit image, you will have 256 intensity levels, and histogram is a plot that shows how many pixels are present for each of those 256 intensity values, right? And by looking at histogram, we can tell, up to some extent, we can tell what kind of an image it is, right? So whether it's a dark image or a light image, or whether it has a low contrast, or whether it has a high contrast, or so on, right? And we also saw that the histogram of a contrast enhanced image, or an image with a high contrast, will have relatively equal values of pixels, which are spread apart or spread along the whole of the dynamic range of the image, right? Then we discussed about what are linear spatial filters, and about the concept of convolution. So again, can anyone tell me what is a box filter? Or an unweighted averaging filter? What do you mean by an unweighted averaging filter? What does it do?
All the weights of the kernel are equal.
Yes, all the weights of the whole kernel would be equal, right? And that's why it's called as an unweighted. And the advantage is that because it's an averaging filter, it will average out all the pixel intensity values, right? So it will look at the neighborhood of the pixels and averages all that and gives a value for the center pixel. So that is what you mainly mean by convolution, right? So in convolution, in the process of convolution, what happens is, given a particular mask, now that mask can be an averaging filter, it can be a Gaussian filter, it can be other edge operators also, which we'll be discussing today. So in the process of convolution, what happens is each of these masks, so let us assume it's a 3x3 mask that we are taking for as an example. So in that 3x3 mask, if it is an averaging filter, an unweighted averaging filter, you can assume the values, the constant values to be 1 by 9, because total number of elements you have is 9. So after normalizing, there is a 1 by 9 value for each of the pixels or for each of the elements in the convolution mask. And then this mask is slided starting from the origin or the top left corner. This mask is slided across the whole image, okay, and the average is taken, the weighted average is taken, okay. So when I say weighted average, what I mean is the convolution mask elements, the values which is present there, is multiplied with each of the elements which are present in the underlying image, and the sum of all that is taken, and it is given as the center pixel value, right? And this is repeated for as the convolution mask is slided along the whole image. So like that you get the filtered image. Now what is a Gaussian filter? Can anyone tell me what is a Gaussian filter? Or how different is a Gaussian filter with respect to a normal box filter?
Now, in this case, we have certain set of weights, and
Yes.
that weights are governed by a Gaussian function.
Yes. So in a Gaussian filter, what you have is it represents, the weights are given in such a way that it represents a Gaussian function. So which means that the center pixel is given more weight as compared to the neighboring pixels. So in the neighboring pixels, as the distance of the neighboring pixel increases with respect to the center pixel, the weight that is given also reduces, right? And we also saw how the spread of sigma, or basically the standard deviation of the Gaussian filter, would affect the weighted averaging, okay. And we also saw some examples. So that's what we had discussed last class. So from today's class, we'll discuss about sharpening spatial filters. So last class, again, this box filter is an averaging filter, the Gaussian averaging filter. All these filters, what it does is basically smoothing the noise by blurring the image, right? And the amount of blur would depend upon what is the size of the convolution mask which is used. And if it's a case of Gaussian, it depends upon how much is the spread of sigma and so on. Now, in the case of sharpening filters, what sharpening filters means is it helps to increase, or it helps to enhance the details of the edges or of any abrupt changes in the frequency of the signals, or in the case of images, it is abrupt changes in the intensity values, okay. So let's say you have an image and you wanted to sharpen the image. When you say sharpen the image, it means to enhance the edge details or the boundary details which are present in an image. Then you can make use of sharpening filters. You can also make use of sharpening filters in order to enhance any blurred details, okay. So after the process of, let's say, smoothing an image or averaging, using an averaging filter, you can use a sharpening filter in order to enhance the edge details which are present. So that is what you see in this diagram over here. Let me just take a laser pointer. So let's say this is an input image, right? And this is a smoothed image. Let's say it's a Gaussian filter was used. But still what you see is that at the edges, okay, especially this side, in these edges, we see that there is some blurring, right? Now, after using a sharpening filter, a sharpening spatial filter, you can see that the edges have been retained. But at the same time, because of the smoothing operation, some of the noise components which are present here has been averaged out. It has been smoothened. Okay, so here also it has been smoothened, but at the same time, this blurring the effect of the blurring over here has been reduced because the edges have been enhanced. So that is the role of a sharpening spatial filter. And it is analogous to spatial differentiation. Okay, just like how averaging is analogous to integration, you can say the sharpening is analogous to differentiation. So basically when you do the differentiation, what you get would be the details of the edges or any abrupt changes in the intensity levels which are present in an image. Okay, so before we go further to learning about spatial filters, we need to understand this concept of how to find the derivative of each pixel. Okay, so first order derivative of one dimensional function, you can represent it this way. So let's say if it's along the direction x, right, dou f by dou x, the partial derivative is given by f of x plus 1 minus f of x if we are taking a finite difference approximation, right? So it is easier to if you understand this, it would be easier for you to just convert that in terms of x y when it comes to two-dimensional function. So when it's a two-dimensional function, you'll have dou f by dou x as well as dou f by dou y, and here what you're doing is taking one pixel ahead minus the current pixel which is in consideration, right? So fx plus 1 minus fx, that would be for the x direction. If it's a y direction, you'll have one more component over here, right? If it's a 2D image. So this is a first order derivative. When you're taking a second order derivative, you can take it as dou square f by dou x square if we are taking for a one-dimensional signal. So here again, if we substitute this particular formula, that is take the derivative of this again. So how we can write here, or how we arrive at this formula, is by taking f of x plus 1 minus f of x minus of f of x minus f of x minus 1, and then when you open the brackets, you will get minus 2 fx there. Okay. So this is a basic concept of finding the first order and second order derivative for a one-dimensional function f of x. So the same can be translated to a two-dimensional signal. Okay, so you can find dou f by dou x, dou f by dou y, that would be along the x direction as well as y direction. So let me represent this dou f by dou x by gx, dou f by dou y by gy, and representing this as a column vector would give me del f, which is basically called as the gradient of an image. Okay, so when I say gradient of an image, what that means is it gives details about any abrupt changes in the intensity. So if you're trying to find the gradient of an image, okay, when you take the gradient, what happens is if it's a homogeneous region, you'll get it as a 0 because there is no changes in the intensity values in a homogeneous region, right? But if the value of the gradient increases as the change in the intensity values increases. So if there's an abrupt change in the intensity value, you'll get a high value for the gradient, okay, for the corresponding pixel in the gradient of an image. So after taking the gradient, what you get is what are the edge details, or what are the high frequency details. Okay, if you're talking about frequency, which we'll discuss later, what are the edge details, any boundary details, even the noise also would get enhanced, or would be filtered out in the sense would be retained in the gradient of an image, and all homogeneous regions would be filtered out. Okay, and this is a formula for that. And one more thing you need to note for a gradient of an image is that it is a vector quantity, which means that by finding the gradient vector, if you take the tan inverse of gy by gx, what you get is the direction of the rate of change which is present in an image. So that also sometimes helps with finding the oriental information in the presence, like in the image. Like for example, if there is some oriental texture in an image, okay, in such cases the directional information will help. But we are not going to that. We'll just look through the magnitude information, how the magnitude spectrum would help when we are finding different when we are filtering out certain noise from the image. We'll see later that one later. Okay, now finding the magnitude of the gradient, you can either calculate it as root of gx square plus a gy square. Okay, you can take the root of the sum of squares of both the gradients gx and gy, or you can also take it as sum of the absolute values of gx and gy. Okay, so that would be an approximate to this, but it will help with reduction in the computation. So that is also another way by which you can find the magnitude. Okay. Now, in terms of formula, we've already seen how the finite difference equation can be used to find dou f by dou x and dou f by dou y, and how it can be expressed, right? Now, there are various edge operators, okay, or spatial filters that can be used to implement the same thing in a much simpler way. That means you can make use of the process of convolution and create masks that will help to filter out the edges. So in the previous class, what we saw was how spatial filters can be used for averaging the images, right? So here we are going to see how the same concept of spatial filters, how it can be used to filter out the edges, filter out in the sense to retain the edges in an image. So let's say this is a particular image that we are considering, okay, and the different pixel locations of the pixels are z1, z2, z3, z4, z5, z6, z7, z8, and z9, right? Now, Robert's cross gradient operator is one of the most simplest gradient edge operator, okay, which helps with finding the edges. And this is one representation of the Roberts operator, where you have minus and one along the along one diagonal as diagonal elements along one direction, and along the other direction you have 1 and minus 1. So let's say if you want to find out what is the gradient along this center pixel Z5 over here, then you can use these masks over here. Okay, so if I'm, for example, if I'm taking this mask and doing the, calculating the weighted average over here, what I get would be Z9 minus Z5, because you have 1 and minus 1 here, right? And that would be gx. And to calculate gy, I can take this mask over here, and what I get would be z8 minus z6. Okay, so by that way you can calculate the gradients gx and gy with the help of Robert's cross gradient operator. But one disadvantage, or one thing that you can observe here is when we are usually when you are doing convolution process using masks or filter masks or convolution kernels, it is preferred to have a mask with a dimension in such a way that you can get a center pixel value, or you can easily calculate for a center pixel value. Rather than taking a 2 cross 2, it would be better to take a 3 cross 3 or a 5 cross 5 mask. Okay, so another operator which gives better results and which can be better used is the Prewitt operator. So in the Prewitt's operator, what you see is this would be for gx, you have minus 1, minus 1, minus 1, and 1, 1, 1 along the top row and the bottom row. And for the gy, okay, operator, you have it as minus 1, minus 1, minus 1 around the first column, and 1, all elements 1 along the third column. Okay, so let's say you're taking the same image with z1 to z9 as elements. How you calculate gx would be, you can just take this mask and keep it over here, right? So you have 1 plus 1 plus 1 here, right? So z7 plus z8 plus z9 minus z1 minus z2 minus z3. So all that I'm doing is I'm overlaying this mask over here and taking the average over there, right? Or taking the total sum, weighted sum. So that is how you get this particular equation here. Same way, to get gy, what I can do is I can put this mask over this and calculate the value. So gy can be calculated as z3 plus z6 plus z9 along this direction, minus z1 minus z4 minus z7. And these two masks, this is called as the Prewitt's operator. Okay, and this value, this particular value that you get would be the gradient information along the center pixel. Now, another modification of the Previtt's operator is a Sorbil operator. So in a Sorbil edge operator, how you see is there is more weight which is given to the center pixel along each row. That is, here it is -1, -2, -1. This is 1, 2, 1. And in this case, for the y direction, it's -1, -2, -1, and 1, 2, 1, right? So accordingly, the equations also change. So this is one difference, and we see that while we are usually using edge operators, if we are using edge operators for finding the gradient of an image, usually we use either the Sorbil operator or the Previtt's operator. Robert's operator is very rarely used. Okay, and as discussed earlier, in order to find the magnitude, you can just take the absolute of gx and gy and just add them together. And apart from finding the horizontal and the vertical information, you can also use masks or modify masks in order to get the diagonal information, diagonal edge information. Like for example, for the Previtt's operator, you can write this as -1, -1, -1 this way and 1, 1, 1 here. In the case of Sorbil operator, -1, -2, -1 here and 1, 2, 1 here, right? So more weight is given to the diagonal elements over here, right? So if we use these masks in order to filter out an image, what we see is that the edges along the diagonals will get enhanced. In the previous masks, what we'll get is gx means along the horizontal direction and gy means the edges along the y direction, that is along the vertical direction would be enhanced. In these cases, the edges along the diagonal direction would be enhanced. So as an example, you can see for this particular image, if I'm applying gx, or if I'm trying to find the gradient along the x direction, okay, I get this particular image. If I try to find along the y direction, I get this particular image. And if I take the gradient, the total gradient, that is sum of the absolute values of gx and gy, I get an enhanced image this way. So if you compare between this image as well as the final image, what we see is that all these homogeneous regions, that means regions where the intensity values are constant throughout, right? All that is black over here. It's filled with black values, or zero pixel values, 0, which means now there is no gradient information which is present here. But along all the edges, the horizontal and vertical edges, okay, here even in the diagonal edges, since this is not just 1 pixel long, it is more than a pixel long, so that information is also taken as the horizontal and vertical information. So all that information is getting retained in this final image. And how this helps is this for example, if you want to apply a segmentation algorithm and you want to enhance the edges of the particular object, okay, in such cases or in any cases where you want to enhance the edge details, you can make use of the edge operators, the edge spatial operators, and as you see, the edges would get enhanced. But one problem is that it's not just the edges, the noise. If there is any noise which is present, then that may also get enhanced. So in order to avoid that, one strategy or one method that you can use is you can first smoothen the image and then apply the edge operators. Okay, so in this particular example, you see that this image has been smoothened, okay, or averaged out. An averaging filter has been used, and then when we take the horizontal and vertical components and add them together. So basically, when you're trying to find the gradient of the image, you find that it is a much better image with the edges alone enhanced and not the noise component. So if you compare with the previous image over here, you see that it is more of edge information that we retain in this image. So you can use a smoothening filter and then find the gradient, or then use the edge operators to find the gradient. Okay, now coming to Laplacian filter. So till now what we had been discussing was about first order filters or first order derivative or first order finite difference approximation or first order derivatives. Now Laplacian is a second order derivative. So just like the previous one, here also you can derive the formulas over here. So if you substitute for the dou square f by dou x square using a finite difference approximation for both this component as well as this component, then you can derive these equations. Okay, so if I express this in terms of a mask, I can write it as minus 1 minus 1 minus 1 minus 1 along if I could say it this way, that is for the center pixel I'll have a value 4. Okay, and along the pixel values which are present in the horizontal as well as vertical direction, it's minus 1. Okay, so this is one type of a Laplacian filter that can be used. Another type of Laplacian filter that can be used where the diagonal elements are also being considered is this particular mask, where the center pixel has a value 8 and all the remaining pixels, the neighborhood pixels, have a value minus 1. So both of these are two different types of Laplacian masks that can be used to find the gradient of an image. And these are the formulas that you get when you try to use the Laplacian filter to filter out the image. Okay, now before we go to the concept of frequency, if does anybody have any doubts so far?
Excuse me, ma'am.
Yes.
Why do we use particular values like in the previous, the Laplace kernel? Why did we the center value was 8 and why not any other value like 10
Okay.
or something else?
Yeah. So here the value is 4 and minus 1, minus 1, minus 1. So we are giving minus 1 weights to the neighbor pixels, right? And we are considering 4 different pixels over here. Just imagine this way. In one of the previous slides, where was it? Yeah. So in this particular slide, if you see, this one is for a one-dimensional function, right? So in this one-dimensional function for dou square f by dou x squared, how did we get this f of x plus 1 minus 2fx plus f of x minus 1? What we had done was we took the dou f by dou x. So dou f by dou x is considered by taking f of x plus 1 minus f of x. So if you consider 2 pixels, you take 1 pixel minus the previous pixel. Okay, or if our pixel under consideration is f of x, we take the next pixel minus the pixel under consideration, right? So, and taking the derivative of that further, then you can take it as f of x plus 1, that is the next pixel minus the pixel under consideration. Okay, and then again the pixel under consideration minus the previous pixel. Okay, so when you take that together, there is a minus of f of x minus f of x minus 1. Okay, open the brackets and you get this. So this same concept you can use in the case of Laplacian also, where both dou square f by dou x square comes, as well as dou square f by dou y square also you will have to consider. So in that case, now if the function for a two-dimensional signal, the function of f becomes in terms of x and y, right? So now this value becomes f of x plus 1 comma y, and this becomes minus 2 of x comma y, and this becomes f of x minus 1 comma y. So that way, when you calculate for dou square f by dou y square, again you'll get a similar equation there. Okay, now this one, if you imagine in terms of spatial filters, that is, let me go to the Laplacian filter. So when you consider this in terms of the spatial filters, then you'll get those values. Like for example, this would be my f of x, right? Now f of x plus 1 comma y, right? That means along, this is f of xy, right? So along the same y, I'm taking x plus 1. That would be this particular component. And along the same row, along the same y, I'm taking f of, sorry, it's not y. It would be f of x plus 1 would be the row, right? Sorry. So f of x plus 1 comma y would be this particular location, right? Minus this one. And then Again, I'm taking this value and taking minus this. Okay, so combining both the equations for dou square f xy by dou x square and dou square of f xy by dou y square, you'll get this. Am I clear?
Yes, ma'am.
Okay, okay. So just take that equation, try to solve that, and then you'll see that you'll be able to find out how these values came over here. Okay, any doubts? Any other doubts? Okay, moving on. Next, we'll go to the concept of frequency. Fine. So when you say frequency in terms of a one-dimensional signal, it basically measures how many cycles per second, right? So in the case of images, it would be, you can think of it as cycles per pixel. Okay, so instead of a time domain, what you're having as a spatial domain. So how many cycles per pixel? In the sense, it's more about how much is the abrupt changes which are happening in an image, right? So when I say a particular region has a low frequency, it would mean that the pixel intensity value variations within that region under consideration or region of interest is less. That means there is not much variation. Okay, but that means it is a slowly varying intensity in that particular region. So that means that is a low frequency. If I say high frequency for a particular image region in an image, what that means is there are abrupt changes in the intensity values. Okay, so in terms of images, low frequency corresponds to the slowly varying regions or the intensity values, whereas high frequency corresponds to the abrupt changes in the intensity. And where all do you find abrupt changes? It may be along the boundary, that is along the edges, and even noise, right? Or even noise could be an abrupt change. So that is also that will also contribute to the high frequency regions or the high frequency details in an image. So if I take this particular image, here all these regions, okay, that would be the slowly varying signals, or these would be the regions that contribute to the low frequency details in the image. And okay, let me take the pointer. Okay, so these would be the low frequency regions or low frequency details, and here all these edges would give me the high frequency details in the image. So when I take the Fourier transform of this particular image, and then we also, while we take the Fourier transform, we also try to translate the center of the Fourier transform to the center of the image. So you'll get somewhat like this. Okay, so this would be the origin in the Fourier transform. Okay, and then you have all the other edge details over here. So around the origin or near to the origin, what we have is the low frequency details, and as we move further away from the origin, we have all the high frequency details in the Fourier transform when we take the Fourier transform of a particular image. Okay, so the Fourier transform of an image can be calculated the same way as that as how we calculate for a one-dimensional signal. The only thing is that the difference is that there will be two different variables, right? You'll have two variables. Now g of xy, if you're considering g of xy as the image, then Fourier transform of the image can be represented in terms of two frequency variables u and v. So x and y are the spatial variables or spatial domain variables. U and v are the frequency domain variables. And same way you can calculate the Fourier transform equation here. The only difference is that in the exponential term, you will have two terms here, ux plus by, because of two different variables, frequency variables, and here also you have dx dy. Same way, when we take the inverse Fourier transform, it is similar to that of a one-dimensional signal. The only difference here is that again you have ux plus vy and two different variables which are used here. Now, when you calculate the Fourier transform, you'll have a magnitude component as well as a phase component, right? So we express separately the magnitude spectrum as well as the phase spectrum, and we process them separately while we process the images, or when we deal with the Fourier transform. And one more thing that we see is that the Fourier transform of an image or of a two-dimensional signal follows the same properties as that of a one-dimensional signal. Okay, so let's consider one example over here. We were discussing about spatial filters, right? Can anyone tell me what a spatial filter is this one? We had just discussed this.
Sorbil.
Could you repeat?
Sorbil filter.
Sorbil, right? Yeah, it's a Sorbil's filter, Sorbil's edge operator, and this is the spatial domain filter. Okay. Now, if I look at this particular, and so if I look at this particular spatial filter, what I see is the values are -1, -2, -1, and 1 to 1. Okay. So if I'm representing this signal or this spatial domain filter in terms of the intensity regions this way, right? I can represent this as so you have 1, 2, 1, and here you have 1, -2, and -1. Okay, so this is the equivalent, okay, transfer function for this particular spatial domain. And I can so this one I can translate it to a filtered frequency domain in this way, where these high values, high intensity values, are given by this white color region here, and these low intensity values or low regions can be low weights can be given as these black regions. Okay, so here these represent higher weights and this represents lower weights. Okay, and if I use this particular filter mask in the frequency domain, okay, in order to filter out the images, I will get this particular image as a result. Okay, I'm taking the same building image as we considered before. Now, if I use this spatial domain mask, okay, on the same image, I'll get this. Okay, so here by this example, all that we are trying to do is in the spatial domain, if we are using this filter, okay, so the Sorbil operator filter, and if we are translating that in the frequency domain and using or doing the same filtering operation, but in the filtering frequency domain, you get identical results. Okay, the results would be the same. But usually there are other operators in the frequency domain. We go ahead with other kind of filter masks, okay, which we'll see later. Now, one thing you have to observe here is that if you're taking the Fourier transform of an image, okay, it actually takes into consideration all the values which are present in the image. Okay, so g of xy is my image. Okay, and if I'm trying to, let's say, calculate at a particular position, say I'm going to calculate what is the Fourier transform of 0, 0, then here to calculate that for any values of u or v, it will take into consideration all the pixel values which are present in an image. Okay, so what it means is if any values in the image changes, then accordingly the Fourier transform, the value of the Fourier transform will also change. So in other terms, what you can say is Fourier transform will help us to find out what is the frequency information in an image, but not exactly, it cannot be exactly used as a representation of a particular image. Okay, because firstly, because any small change in any one location of an image will change the whole of the Fourier transform over here, right? So therefore, the any changes in one particular image would not reflect changes in some particular location, right? It makes changes in the whole location. So that spatial information or the spatial changes that cannot be represented in case of a Fourier transform. Okay, and in such cases we go for if we have to represent a particular image where we need both information of both the frequency changes, but at the same time where exactly is the spatial location of those changes, then we go ahead with techniques or transforms like wavelet transform. Okay, but Fourier transform is preferred when you know what is the noise present in the image and what exactly or what exact is the frequency of the noise which is present in an image. Or let's say you know what are the specific frequency locations or frequency spectrum, frequency band of frequencies which needs to be rejected or discarded from an image. In such cases, you can go for a Fourier transform, where the spatial location of the particular details does not matter. Okay, now F00, can anyone tell me if I take the Fourier transform at locations, so 0, that means the Fourier transform of 0, what does that give me, or what does it contain? What is it exactly in terms of the image? Okay, if you look at this particular equation, when I take Fourier transform 0, I'm taking u as 0, v as 0, so this goes as 0, this goes, right? So what remains here is basically the integral, double integral of gxy dx dy, right? So it is as if you're taking the average of the whole image, right? So F00, which is basically the origin of the Fourier transform, would give me the information of the average frequency of the whole image. Okay, so if I just take this particular Fourier transform which we were looking at, I said this is the Fourier transform after translating the origin of the Fourier transform to the center, right? So this is my F00 right now. And this particular frequency represents what is, or the value at F00 would represent what is the average intensity or the average value of this particular image. And average value, basically what that means is here you have the slowly varying signals or the low frequency signals over here, and here the high frequency signals which captures all the edge details of the image. Okay, you'll understand this better when we go through some filters. Okay, so keeping the concept of the Fourier transform of an image in mind, if I want to use a low pass filter, or if I'm using a low pass filter, what would happen to an image? Let's say I'm considering an ideal low pass filter, and this is the equation for that. So what that means is, let's say D0 is a certain cutoff frequency that I'm using. And within that cutoff frequency, I have a value 1, and for all the remaining part, I have a value 0. And this is my ideal low pass filter. Okay, I call it ideal because it's a 1 and a 0, or what that means is I have a white pixel and a black pixel. It's an abrupt change, right? So if I visualize that in terms of the 3D topology, what I see is I have a high value here and an abrupt change to the black pixels over here. So if I'm considering an ideal low pass filter, and let's say with D0 cutoff, okay, so that D0 can be any value. Now, what exactly happens? So if I'm using this particular filter in order to filter out the frequency transform of a particular image, of any image, can anyone tell me what exactly happens, or how the filtered image would look like?
Can you repeat the question?
Okay, the question is, this is a low pass filter, an ideal low pass filter, right? I'm using this filter to filter out an image in the frequency domain, right? So that means this is my filter mask in the frequency domain, okay, because I have U and V and I'm representing it as HUV. And let's say I have a Fourier transform of my image, which is represented by capital FUV, right? And I'm multiplying both of that, right? So that means I'm basically doing a multiplication of both the Fourier transform of both the mask as well as the original image, right? The frequency transform of the original image. What do I get? Or how would the output image look like? So after doing the filtering process, when I reconstruct the image back, what do you expect the resultant image to look like? Any guess? Okay, so we know that this is a low pass filter, right? So you're passing all the low frequencies here. Now, I said, and if you observe here, what you see is that towards the center, you have these white pixels or the high values, okay? And in the background over here, you have it as black pixels. If I take the Fourier transform, let me go back here. I said that this is how the Fourier transform of this particular image looks like. Now let's say I'm using that, the previous filter which I showed, I'm using that over this particular filter to filter out the low frequency. So what happens is that the low frequencies would get filtered in the sense that would be passed, and the remaining high frequencies will get removed or discarded, right? So when I'm using the low pass filter, what happens is basically what I'm doing is I'm passing the low frequencies in an image and filtering out or removing all the high frequencies present in an image, okay? So low frequencies in an image correspond to the slowly varying information or the slowly varying pixels, and high frequency corresponds to removing the edge details, right? So that would mean that is equivalent to a blurring operation, okay, because you're removing out the edge details, okay, and you're retaining only the slowly varying signals. So what a low pass filter does for an image is that it would basically average out the signal. And how much would it average out, or how much would the blurring happen, would depend upon what is the cutoff frequency that you consider. That is the value of d0. And in this particular example, what we see is this is an original image. And if I'm taking a radii of 10, okay, so this is for a radii of 10 and this is for a radius of 30, okay. So what happens is for 10, as we see, the distance is lesser, right? So you have most of the edge details which are removed. But at the same time, when you have a larger radius, so when I say radius, what I mean is for this particular radius, right? When I have a larger radius over here, what happens is more of the edge details is being what retained as compared to the slowly varying signals over here. Okay, I'll just go further with another low pass filter. Now, the previous one was an ideal low pass filter. In the case of Gaussian low pass filter, you can observe that it will be slowly varying. You don't have an abrupt cutoff frequency as such, right? It is a slowly varying. So you have this gradual change from the high value to the low value. So this is how the Gaussian low pass filter would look like. And for different values of sigma, right, here in this case d0 would represent this particular sigma, right? So for varying values of d0, what happens is the spread keeps increasing, okay. So this is for d0 10, this is for d0 is equal to 60, and the spread increases. So for a lower spread over here, what happens is there is this particular circle that you see over here, right? It is smaller in size, and as the spreading increases, you see that this would be increasing further. Now, if I'm applying this particular Gaussian low pass filter to an image, again, depending upon how or how much is the spread, the blurring also changes, right? But one difference you can see with respect to this low pass filtering using the Gaussian filter as well as the previous previous ideal low pass filter is that in the ideal low pass filter there were some contours, kind of contours which were formed at the edges, which was undesirable, right? But if you're using a Gaussian low pass filter with a slowly changing or gradually changing intensity values, one thing or one fact that you observe is that the blurring would accordingly be controlled. Okay, it would be more of a smoother blurring. So before we go to high pass filter, uh, is the concept of low pass filter clear?
Excuse me, ma'am.
Yes.
Ma'am, what is the range of the radius of low pass filter in this case? Like what is
Okay. Yeah,
what
you can have okay, so I'll just explain with respect to this particular image. You can have a high whatever range you want, you can have a high range, but always there is a limit to how much we try to increase. Like let's say for example, I can take, instead of 30 I can take it as 60, I can take it as 100, but as I'm increasing the range over here, what happens is more and more details of these edges creep in. Okay, again, there is more, still we don't get exactly the same image. It would be more like false contours that happen here. Okay, so how we select a value for D0 would depend upon what is the kind of blurring that you would like. Like for example, for this particular ideal low pass filter, it's not like if you're taking this particular image, okay, it's not recommended to go beyond 30 and not even 30, right? And if you're going for a Gaussian filter, okay, here also as the spread increases, the values also keep changing. So if I'm looking at this particular image, there is a purpose for which why you want the blurring to happen. So in some cases you may need a blurring to be done in order to find out what is the average background. Okay, maybe it is to estimate the background in a particular image. In such cases you want a very high amount of blurring. Okay, but in some other cases you do not want to estimate the background. Only thing you want to do is just smoothen out the noise. In such cases you can go for a lower spread over there. Okay, so here always the spread of the Gaussian filter and the size of the Gaussian filter would always depend upon how much of blurring you want the resultant you want to have in the resultant image. Is that clear?
Yes, ma'am. Yes, ma'am. I
Okay.
understood that. I was asking like what is the maximum value that we can put for the radii in the ideal filter? Like there should be some upper limit. Like if we put that value, then all of the frequencies will pass basically. Like all pass filter. Like what will be that radii?
Okay, so in that case, if you're asking, then this particular value should be within the whole of this image if you want everything to pass through. Okay, because here what you have is the low, this average value of the particular image, and here what you're having is basically all the high frequency details, right? So there is no specific value for the low pass filter, because it depends upon what is the cutoff frequency, right? But let's say again, if you want an image, if you want to know what happens when you're taking the maximum radii that could be fitted onto this particular frequency mask, then what happens is all the edge details would be that would be passed through. Okay, and another thing you want to note down is, again, the value that you choose over here for the radius, that would also depend on what is the image that you're considering. So maybe your image do not have much of edge details, maybe your image has got a lot of edge details. Like for example, if you're taking the case of a text written, if it's in the form of a text, there may be too many edge details or the frequency details, right? So depending on that also the radius would change. But as you said, is there an upper limit? If you're taking the maximum value which is possible for this particular image, or for this particular mask, what happens is all the edge details would be filtered in, or that would be passed in. Okay, but that is not something which we desire. What we are doing with, or what is our aim with using a low pass filter, is basically for blurring out an image, right? And and for that, finding the ideal value or the exact value for this particular cutoff would depend upon the image that you have. How much of details would be present in the image? So instead of this image, let's say if it is some natural image where there is not much of variations. Okay, in that case, the values that we use, okay, because you do not have much of high frequency details over there. Okay, so therefore you might need a much lower value of the cutoff is sufficient for such a kind of image when you're trying to smoothen that out. Does that answer your question?
Yes, ma'am. Now, on the previous slide, what exactly U and V are? Like, what does those points mean in the previous slide?
Is this line?
Yes, ma'am. U and
Okay.
V. Like, are these
Here.
pixel points? Or...
Okay, no, U and V are basically the frequency variables. This is the frequency transform, right? So in this frequency transform, these are U and V are the variables in the frequency domain. So X and X and Y you're using for spatial coordinates of the image, okay, and U and Y are used for the frequency domain. So here we are talking about frequency filters. We are not talking about spatial domain filters. So in the frequency domain, right, what we're doing is, let's say you have the Fourier transform of an image in a frequency domain, right, and you have a filter, a low pass filter in the frequency domain itself, and you're multiplying that. So here what we're discussing is all the operations is in the frequency domain, right? So that is why you are using these variables U and V, and this is basically the Fourier transform of the particular filter that we are considering. This is in the frequency domain, that's why you have it as U and V. Is that clear?
Yes, ma'am. So it's like if we do a Fourier transform along the x-axis, so we get U, and if we do it along the y-axis, we get V. So together we have U and V.
Yes, together it is U and V. But it's like taking the whole. Okay, let me go back to this particular. Okay, this is the Fourier transform equation, right? So here, let's say if I'm taking the Fourier transform in one dimensional, okay, I can take it as f of k. Okay. So if I take f of k is equal to, and let's say instead of xy, I'm taking it as t over here, right? So here t represents the time domain and k represents the the frequency domain, right? And you have these in terms, or the integration is done in terms of d t over here in the case of one dimensional, okay? So you can think of the same thing being translated in the Fourier transform. Only thing is that you have two different variables here, which would be dx, the integration along the x, and the integration along the y, okay, and correspondingly you will have two different variables, a 2D signal in the Fourier domain, which is represented by u and v. Is that clear?
Yes, ma'am. Thank you.
Okay. Any doubts? Anyone else? Okay, moving further. For a high pass filter, the concept is the same. Only difference is that instead of having high values for the low frequencies, you'll have high values for the higher frequencies, because it is a higher frequencies that we want to filter out, right? So again, the high frequency filters you can represent by this particular equation. That is, if it is a normalized filter, I can write it as 1 minus the filter transfer function for a low pass filter, okay? So for an ideal filter, this would be the equation. So all that you're doing is 0 and 1 is exchanged, and this one is for the high pass filter Gaussian, okay, where you take 1 minus of the corresponding low pass filter equation. Now how that looks like would be here. In the ideal case, it would be high values for the higher frequencies and low values for the lower frequencies. So in the ideal case, it's an abrupt cutoff, right? So at D0, you have this cutoff, right? And you have high values for high values in the sense, since it is, if it is normalized, you have it as 1. for the high frequencies and the low values for the low frequencies. Okay, and this is a case of a Gaussian filter, where again you see that there is a gradual change of the intensity, not intensity, a gradual change in the values along the filters, high pass filters in the frequency domain, and this is a corresponding representation to visualize that. Now, how the images would look like is, if you're using a high pass filter, as I said, the high pass filter passes the high frequencies in an image, and when you see high frequencies, what it means is abrupt changes in the intensity values in the image. And where all do you have the abrupt values? You have it along the edges or the boundaries or even the noise, right? So these are some examples of using a high pass filter. This is the ideal high pass filter, and this is the case of a Gaussian high pass filter, right? So what we see is the edge details are retained in the image, whereas all the underlying average value which is present in the image has been filtered out, right? Or the background values which you have has been filtered out, and only the edge details are present. And again, one difference between ideal high pass filters, because of this abrupt cutoff that you have, again there will be some false contours which are present in the image, okay, along the or near the edges. Whereas in the case of a Gaussian high pass filter, since the change from high to low is gradual, you see that there is more of a smooth image over here with lesser, there is no false contours, and there is a lesser noise which is present in this image. Okay. And by high pass filter, what you do or what you want is the edge data is present in the image. Now, how that helps is, like as an example of an application, let's say you have this is the original image, okay, and this is kind of a smudged image of a fingerprint. So what you observe is there are some patterns which are present, but because it is smudged and you have uneven background values or background distribution, you can't exactly make out what is the pattern which is present over here. So to better filter out these edge information or this pattern which is present in the image, you can make use of the high pass filter. So this is the result of the high pass filter, and when you threshold that, you'll see that the patterns become much more easier to judge or easier to recognize as compared to this original image, and the background variations that were present has also been removed with the help of the high pass filtering. So just a very simple example on how you can use the high pass filtering for pattern, finding out or recognizing the pattern, or for further texture analysis. Okay, coming to another application is the band reject filter. So band reject filter means along the particular band, okay, what all frequencies come along this particular band, those frequencies alone would be rejected, okay, and all the other frequencies would be retained. This is the case of an ideal case where you have the a sharp cutoff frequencies, and here this is the case of a Gaussian where you have gradual changes along this direction as well as this direction, and it would look somewhat like this. So where you can make use of or where band reject filters help is when in a particular image, if you are having some periodic noise, okay, so in if you have a particular Fourier transform where you can understand or you can identify what is the exact frequency components of the noise components which are present in the image, then we can make use of the band reject filter. That means you can reject only those particular frequency components which are present in the Fourier transform. Like for example, in this particular image, what you see is there is the noise components which are present here has a particular pattern, right? So this particular information can be captured with the help of Fourier transform. If you look at this Fourier transform closely, what you see is you see certain dots, okay, over here, and these are basically the frequencies which are contributed by the noise, right? So in order to remove these frequencies or these frequency component of the noise, what I can do is I can design a band reject filter in order to reject only those particular set of frequencies, because if you look at these frequencies, it lies along a circular pattern, right? So accordingly, a circular pattern can be designed for the band reject filter, for only those set of frequencies to be rejected. And after rejecting those frequencies and retaining the remaining frequencies, if I reconstruct the image back, I would get it in this form. Okay, so this is an example of how you can use band reject filters, but you can make use of band reject filters only if you know where exactly or what exactly is the frequency at which the noise components contribute. Okay. Now coming to sampling and aliasing. So sampling is a concept that we already saw in the previous class. Basically when you take an image, you have continuous signals which are present in the image, and you sample those image into, to get the different pixel intensity values, and you also quantize that, right, to get the discrete image or the digital image. Now, depending upon how you take the samples in a particular image would is also important to know whether we are able to capture the exact image or not. Okay, and the sampling and aliasing also has an important role when it comes to resampling an image. There would be some cases where, let's say, you have a large image and you want to resample that to a smaller image, right? So in that cases, what is the exact number of samples, or what is good sampling? Okay, that becomes a question when you're working with resampling techniques. So if you observe these two images over here and these two images over here, what we observe is that in these two images, you do have at least one sample in every, this is a checkerboard image, right? So in every square, you have at least one sample which represents that, right? But in this case, these two are cases of undersampling where there are not enough samples to represent all the squares which are present in the image. So just an example of sampling. And just like how you have in one dimension, where if this is a continuous time signal, you take the samples along that, okay, and this would be the sample signal. Same way for a two-dimensional signal also, if you're considering a 2D object over here, and let's say this is the image plane wherein this is projected to, right? So when you take the 2D samples, you'll see it as, you can imagine this as a bed of, 2D signals over here. Okay, so basically it is in this particular example, it is regularly spaced. Okay, and you can take samples along this regularly spaced grid, rectangular grid. But not always is it along a particular rectangle grid. Like for example, if you take the human visual system, the retina is not exactly a rectangular shaped one. Okay, but as far as the normal image capture is concerned, okay, in a normal camera, it's a regular rectangular grid which is used for taking the samples. Okay, and this is the image plane which represents the particular projection of the image being taken. Okay, now this is something which I already discussed. Moving on, so aliasing. Aliasing is a concept which you are already familiar with previously, right? So when you are taking the Fourier transform of a signal, what happens is basically when you take the Fourier transform, there would be a copies of the Fourier spectrum which is obtained at the intervals, right? Like for example, if this is the signal and you're taking the Fourier transform, you get the magnitude spectrum over here. While you sample the signal, there is the copies of this spectrum which you obtain here, right? Now, if you're having the copies of the Fourier transform in this particular way, that means there is a space, there is a sufficient gap between the different spectrum, then it is easier for us to filter out or just take one particular sample out, right? Filter out this particular sample and then reconstruct the original signal. So after reconstructing the signal, you get it in this way, right? But what happens if there is an overlap, and when does that overlap happen? Like for example, let's say this is a case of an undersampled case, right? And then when we take the Fourier transform, what happens is there would be an overlap of different of the Fourier transform, right? So if there is an overlap, what happens is when you try to take or filter out the Fourier transform, right, you might lose some details, right? And you won't be getting a faithful representation of the original signal when you're reconstructing that. Okay, so that is what you call as aliasing. Is the same as that in one-dimensional signal. The same concept can be thought of in the 2D signal also. Okay, where when you're taking the Fourier transform, okay, if there is an undersampled case and there is an overlap between the Fourier transforms, then there won't be a faithful reconstruction. So basically, it's the Nyquist rate. The Nyquist criteria or the theorem has to be followed. Okay, so let's assume that this is an image. It's a 256 cross 256 image. Okay, and I want to resample. I'm resampling this. Okay, to get a 128 cross 128 image. So when I'm resampling, what I'm doing is I am taking only the every second pixel, okay, from this original image. So by taking only the every second pixel of this particular image, I'll get a 128 cross 128 image, and then I'm rescaling that in order to fit it into the exact size as this one. Okay, so as I repeat this process for 64 cross 64, again I take every second pixel from this particular image and then try to resize that. Okay, and I get this one. So what happens is, now in this image you'll see that certain details over here is it's getting lost. Okay, especially at this side. Again, when you take 32 cross 32, again further the details are being lost. Okay, and when it comes to 16 cross 16, you see that the whatever details that we see is completely different from what is present in the original image, right? So this is one example of how resampling or taking every kth sample. Okay, if I'm considering k as a distance, taking every kth sample would not give a good reconstruction. Okay, like for example, let's look at it in terms of the Fourier transform. So let's say if I'm taking a 256 cross 256 image, this image, and this is the Fourier transform of that, right? Now, when I take every second sample from this in order to reduce the resolution or the dimension by a factor of 2, right? I get a 128 cross 128 image, and the corresponding Fourier transform would look somewhat like this. So here, what happens is this is the Fourier spectrum, one spectrum, and here you see that there are copies of the spectrum that you'll see here, 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 and so on. Now, when you further try to resample that by taking the every fourth pixel, in this case that would be 1 by 4, what happens is again there would be copies of the samples which comes, right? And each time you take every kth pixel, the copies, the number of copies keeps increasing and it keeps overlapping also. Okay, so at one particular point it keeps overlapping to such a point that the original details are completely lost in the image. So taking every kth pixel for resampling an image is not a good choice. Okay, so instead what you can do is you can go ahead with anti-aliasing filter in order to first smoothen out the image and then go with the subsampling process. We'll see how that's done. So let's say I'm considering this particular image, and let's say this is an image of a very high dimension. And if you look at this image, what you see is there are a lot of details in this image, right? So even in the background you have a lot of details in here, and along each and every region, if you take the sub-region, there's a lot of edge details or a lot of high frequency details which are present in this particular image. So such images with high frequencies would be highly affected when you do a resampling case, as we'll see next. So this is an example of if I resample this by taking every second pixel along the original, I'll get somewhat like this. Okay, so here there is no aliasing effect that has happened. Okay, and it is fairly a good representation of the original signal. When I take 1 by 4, that is, I'm taking every fourth pixel. Okay, there is some amount of overlap because of which some information is lost. Okay, and when I reconstruct the signal back, I see that I lose some of the information which are present. And when I take 1 by 8, that is taking every 8th pixel, okay, taking the samples which are present only at every 8th pixel, I further lose more information or details which are present in the signal. And this is because of the aliasing that happens. So one way to overcome this is by using an anti-aliasing filter, and we can make use of a Gaussian filter for this. Okay, so the Gaussian filter, the Gaussian low pass filter, that would help removing this kind of ambiguity when it comes to resampling. Okay, so what it does, or what is, by resampling, okay, the range is reduced to u less than half and v less than half. Okay, when you are trying to take the second sample, right? And what you're trying to do is you're trying to remove the contents or remove the frequencies which are outside this particular range. Okay, and therefore trying to prevent any overlap that may happen, right? So by using a Gaussian filter, let's say this is the Gaussian filter for 1 by 2, that is taking every second pixel. So that means I apply the Gaussian filter first and then take subsample it by 2. This is after doing a Gaussian filter and subsampling by 4. This is after using a Gaussian filter and subsampling by 8. Okay, so what you see here is that it is a little blurred. Okay, as and when it keeps on increasing, or when the subsample size increases, size in the sense the pixels increases, there is more blurring that happens, as well as the dimension also reduces. Okay, but at the same time, the basic information of the image is still retained, and it is much better than that of just taking the kth sample alone. So, after resizing the Gaussian filter for 1 by 4 and 1 by 8, this is how it looks like. Still, there is a, I won't say it's an exact faithful reconstruction. The edge details are lost to some extent, but still it is much better than this particular previous case, which we saw, where we just take the subsamples alone, right? So this particular concept where you take an image and then blur it using the Gaussian filter and then subsample it, okay, to get a lower dimension, and again you can again further blur it out using the Gaussian filter and then subsample it, and so on. What happens is you are basically decomposing the signal into various components, right? And these particular components, okay, it still retains more of the average information which is present in the previous image, but at the same time reducing the dimension. Okay, so this particular structure can be called as the Gaussian pyramid. Okay, this is an example of that here. So another example where you take an image, okay, blur it using the Gaussian and then subsample it to get this. So what I say is, let's say if this is a 256 cross 256 image, okay, this is after subsampling it and by a factor of 2, and this would be 128 cross 128. Again, after subsampling, you'll get it as 64 cross 64. Again, 32 cross 32, 16 cross 16, and this goes on. Okay, so you can create up till 1. So this particular structure where each of the levels would represent a particular resolution of the image. So this is the highest resolution, okay, and it can go up to very low, up to 1 pixel. Okay, that would be the lowest resolution, but we don't make use of that 1 pixel. Anyway, so you have the lowest resolution, right? So this particular structure is what you can call as a Gaussian pyramid, and it helps with decomposing a signal or an image to various resolution levels. So this is another representation or illustration of how you can show the Gaussian pyramid, where this is level K, okay, and it can go up to level 0. So let's say if you have an image which is n cross n, okay, and n can be represented as 2 raised to k, then you can have images which ranges from 1 cross 1 to 2 cross 2, okay, up till 2 raised to k cross 2 raised to k images. And this is how it would look like, where you have an image and then various resolution of the images. Okay, is there any doubt so far?
Huh?
Yes.
Can you please explain that thresholding part in the Gaussian one, that u magnitude of u is less than half and that thing?
Okay, okay. Let me see where it is. This slide, right?
Yes, ma'am.
Okay. So here, let's say you have an original image. Okay, here it's written Gaussian 1 by 2. So let's say you have an original image, right? When you're subsampling that by 2, okay, what you're doing is you're taking every second pixel out of that, right? So the Fourier, if you're taking the Fourier transform of the original image, the center of that image, okay, would be, let's say, at u and v, a particular location of u and v. So you can consider u and v as the what to say, frequency. As I said before, those are the frequency variables. Let me see if I can find that. Okay, I'll just use this particular example over here. So let's say I have the dimensions, the variables u and v, and as I said before, these u and v are frequency variables that are used to represent the frequency domain, right? And now in this particular domain, let's say I have an image. You can take any image over here. The image that we were considering, that image also you can take. Now u and v are specific, specific integer values, right? So you have it as 0. It starts with 0, 0, and then you have values which goes from 0 to let's say if it is mn, some value. If it is a 256 cross 256 image, you have right from 0 to 256 over here, and each of these values of u and v would be integer values. Okay, so when you are,
These are, excuse me, ma'am.
yes, yes.
Ma'am, why will it be till 255 or 256? These are the Fourier values, right? Not the
Oh,
special.
yes, yes, yes. These are the Fourier values. Yes. Okay. Sorry about that. Yeah. So if it is a normalized case, yes, the values would be from, usually for the frequency domain, we consider the normalized cases. So it would be from, let's say, from 0 to 1. Okay. Okay. Okay, this value, okay, what exactly is the value that could be obtained when you have 256 cross 256 in the frequency domain is something which I'll just check and let you know, okay, how that's going to be. But when you're using a filtering operation, as I said before, you usually normalize that and find it out. But regarding an image of a particular dimension, when you're taking in the frequency domain, how exactly or what exactly would be the values of u and v, I'll just try to find that out in the normalized case. No, not in the normalized, in the
I guess
unnormalized
that should
case.
depend on individual image.
Yes, what
That's,
is it?
I guess that should depend on like individual image. Like each image will have different
Yes.
frequency ranges.
Yes, yes. It should depend on the image. I mean, it should vary. It would vary according to the image, and that is exactly why we are using a normalized filters also in these cases. Okay, yeah. So coming back to your question, anyway, this one I'll just refer and I'll let you know about this particular thing. Okay, coming back to your question, what was your question here? Okay, so here when you're taking the original Fourier transform, when you're subsampling it, okay, by a factor of 2, okay, then I could say that whatever range you have for u as well as v is coming within the range of 1 by 2. Okay, so that means every second sample that I take, or every yeah, within every second sample, or if I say that I am zooming it in such a way that I reduce the dimension by a factor of 2. Okay, so in that case what happens is the range of values which are present in this u and v is also halved, right? So the Fourier transform which you are considering, it's as if that Fourier transform is being shrunk or compressed by a factor of 2, right? So here the values of u and v, okay, would also be halved, whatever is the corresponding values that you have, right? Now what you're doing with an anti-aliasing filter is you're trying to remove whatever contents or whatever frequency components are present, okay, outside this particular range, so that when you're doing the sampling process it does not cause any overlapping of the copies. Okay, that means it's as if you are cutting out certain information beforehand in order to ensure that the copies does not get overlapped. Okay, is that clear?
Yes, ma'am.
Okay, so it is, what it's doing is since there is an aliasing that happens with the sampling, okay, as a measure to ensure that this aliasing does not occur, we are using an anti-aliasing filter, right? And by using an anti-aliasing filter, what you're ensuring is that these copies does not happen. So this again, there would be blurring when you're using a Gaussian, definitely, or when you're trying to use this anti-aliasing filter, there is definitely a blurring that will happen, okay? But still the information that you have, or the aliasing that is occurring, can be controlled up to an extent. But there is definitely it's not a complete faithful reconstruction, but definitely the edge details are lost as you as the resolution or the as the dimensions keep reducing, as you keep on subsampling it further. Okay, but the aliasing, the effect of aliasing would be reduced. Does that answer your question?
Yes.
Okay, any other doubts? Okay, then we'll stop with the lecture class today.